Hello everyone, it's Chemicator. Welcome back to the second episode of Synthesis Studio. If you are new here, I created this series to help students level up their understanding of organic chemistry in a clear and approachable way. In this episode, we'll tackle 3 high-level challenging problems involving ozonolysis, hydroboration, and epoxidation, with a special focus on stereochemistry. By the end of this video, I hope you will see these reactions and organic chemistry as a whole from a fresh new angle. Now let's work through the first question. This question asks you to rationalize why glycoside A can be oxidized by ozone, but glycoside B actually remains unchanged. First, let's understand the mechanism of the reaction. You're probably already familiar with ozone oxidizing alkenes, a process known as ozonolysis. Interestingly, ozone can also oxidize acetals to produce an alcohol and an ester. Mechanistically, bipolar ozone attacks a carbon atom, while at the same time another oxygen abstracts a proton. In the next step, the bonding electrons between the oxygen and hydrogen moves toward the oxygen-oxygen bond, which leads to the formation of a carbonyl group, followed by elimination of one of the OR groups. As a result, oxygen is released in this reaction. Now let's go back to our case. Ozone cannot react with the compound that has a cis conformation. In contrast, it reacts smoothly with the compound where the hydrogens are trans, producing a lactone with a side chain hydroxyl group. So it seems like this reaction is sensitive to the conformation of the molecule. To find the answer, let's explore the conformational effect using a cyclic model. In theory, an acetal group can exist in 6 different gauche conformers. However, only 3 of these conformers react with ozone. But what is the common feature of these 3 conformers? If you look more closely, you will see that the common feature is that each oxygen has a lone pair n-tied to the carbon-hydrogen bond. This unique arrangement of non-bonding electrons and the carbon-hydrogen bond make the carbon-hydrogen bond weaker than a normal one. This effect can be illustrated by showing the lone pair donating into the carbon-oxygen bond while the hydrogen is kicked off. As a result, the molecule can be oxidized more easily. This interesting phenomenon is called the Stereoelectronic effect. Now let's move into 3D space to fully understand the conformational effect. In glycoside A, the 2 hydrogens are trans. In this conformation, one of the non-bonding electron pairs on each oxygen is n-tied to the adjacent carbon-hydrogen bond. This geometry sets the stage for the stereoelectronic effect. In other words, the interaction between lone pair electrons and the carbon-hydrogen bond weakens the bond, allowing ozone to easily insert into the carbon-hydrogen bond and oxidize the compound. However, when the hydrogens are cis, there is only one pair that can interact with the carbon-hydrogen bond. This limited interaction is not enough to significantly weaken the bond, so ozone cannot effectively oxidize the molecule in this conformation. Notice that, unlike acyclic acetals, a cis-fused ring system is rigid and cannot convert into the trans conformation. In other words, Face-Selectivity arises from the locked conformation of the ring. In the second question, this compound containing a double bond undergoes a hydroboration reaction. You are asked to determine the product and explain the stereoselectivity. This stereoselective hydroboration is part of the total synthesis of monensine, reported by Kishi in 1979. Hydroboration produces organoborane compounds that can react with a variety of reagents to yield useful products such as alcohols, amines, or alkyl halides. The most widely known reaction of organoboranes is their oxidation to form alcohols from alkenes. Mechanistically, hydroboration proceeds via a 4-member transition state in which the hydrogen and boron atoms add to the same face of the double bond. After oxidation, the alcohol group is introduced without altering the stereochemistry. In theory, borane can add equally to either the top or bottom face of the double bond, resulting in a racemic product. But the art lies in controlling this addition in such a way that one face is favored over the other. Traditionally, this bias is introduced by pre-installing a chiral group adjacent to the double bond. If the molecule prefers a certain conformation, it creates a facial discrimination, guiding the borane to attack from the less hindered face. In the reaction presented in the question, the double bond undergoes hydroboration, introducing 2 new chiral centers. Note that this is an anti-Markovnikov addition, meaning that borane adds to the less substituted carbon atom of the double bond. After oxidation, a hydroxyl group is installed on the molecule. Also keep in mind the syn addition of the alcohol and hydrogen atoms in the final product. Now let's discuss the stereoselectivity of this transformation. Calculations indicate that the most stable conformation is achieved when the furan substituent is positioned above the plane of the double bond. As a result, the upper face becomes strictly hindered, making it inaccessible to the nucleophilic attack of BH3. Consequently, borane prefers to approach from the opposite face, avoiding interaction with the bulky substituent. The observed 8:1 diastereoselectivity originates from this preferred conformation and the presence of the bulky group on the adjacent chiral center. This phenomenon is known as Allylic strain, and it plays a crucial role in asymmetric synthesis. The steric interaction between the substituents near the double bond influences the stereochemical outcome of the reaction by restricting access to one face of the molecule. If you are interested in more examples of asymmetric synthesis, check out the total synthesis of gluconic acid, a classic case that showcases how conformational control and steric effects guide selectivity. Now let's go through the last question. Here we are looking at the selective epoxidation reaction. Olefins can be oxidized by peroxy acids to form an epoxide ring, which is highly useful functional group for further transformations. In this particular compound, there are actually 2 double bonds that could potentially undergo epoxidation, but only one of them reacts preferentially. If you look closely, the chlorine atom is positioned near one of the double bonds, making it more reactive under epoxidation conditions. This raises a key question. How does the presence of chlorine increase the reactivity of that double bond? Before we continue, pause the video and think about how stereoelectronic effect involving the chlorine atom might lead to this reaction selectivity. First, let's take a look at the mechanism of epoxidation. Once a peracid approaches an alkene, first the pi electrons of the double bond attack the anti-bonding oxygen-oxygen bond of the peracid. At the same time, the non-bonding electron of this oxygen attacks another carbon atom of the double bond. At first glance, it might look like kind of nonsense, so try to see what happens in the perspective of orbital interaction to feel more comfortable with that. Again, at the same time, sigma electrons of the oxygen-oxygen bond go to the carbon-oxygen bond, and the carbonyl group attacks the hydrogen attached to the oxygen. Notice that these all occur at the same time. As a result, one of the oxygens of peracid is transferred to the double bond, and the peracid is converted to carboxylic acid. The most important thing about the reactivity of alkenes is that more electron-rich alkenes react more rapidly with peracids. For example, this molecule contains 2 double bonds. Upon treatment with the peracid, the double bond in the ring reacts more rapidly than the other double bond because it has more substituents that push electrons toward the double bond. So it's more electron-rich than the other. Now let's go to our case. In this compound, the 2 double bonds are not equivalent. one of them is more electron-rich than the other, so it reacts preferentially with the peracid. But as you see, the number of substituents attached to the double bond is the same. So what factor makes this double bond more electron-rich? The answer lies in the orbital interaction of the CCl bond. Let's focus on the molecular orbitals of the CCl bond. In bonding orbitals, the electron density is located between the atoms. However, in anti-bonding orbitals, the back lobe of the orbital extends outside of the region between the atoms. In our case, the CCl bond is positioned in such a way that the p orbital of the double bond interacts with the anti-bonding back orbital of the CCl bond. In other words, the pi bonding electrons are transferred into the empty sigma star of the CCl bond. It's a beautiful example of electron delocalization. From another perspective, the 2 pi electrons in this double bond are delocalized over 3 atoms. So it's actually a 2 electron free center system. In contrast, the 2 pi electrons in the other double bond are confined between just 2 carbon atoms. Now you can deduce that this double bond is more electron-rich, so it reacts more rapidly than the other. Personally, I really love this last example. Let me know which of the question is more interesting to you by leaving a comment.